Welcome to the bond enthalpies video. By the end of this video, you should be able to explain how bond enthalpies relate to endothermic and exothermic reactions, explain trends in bond enthalpies, and be able to calculate enthalpy of reaction using bond enthalpies. A bond enthalpy is the energy required to break a bond. Since bond breaking is a reversible process, bond formation releases energy, so bond enthalpy also corresponds to the amount of energy released when that same bond forms. It's usually measured in kilojoules per mole. So for instance, here we have a bond between molecules A and B. If we want to break that bond, we have to put energy in to do so. The energy required to break that bond and take apart A and B is the bond enthalpy. If you think about that reaction in the reverse direction, then the bond enthalpy also corresponds to the amount of energy released when a bond between A and B forms. Higher bond energies indicate stronger bonds. This should make intuitive sense. The stronger the bond, the more energy you need to put in to break that bond, or the more energy you'll get out when that bond forms. Typically, as the number of bonds or bond order increases, bond length decreases and strength increases, meaning single bonds are weaker and have smaller bond energies than double bonds, which are weaker and have smaller bond energies than triple bonds. Here's a table of average bond energies. Again, they're reported in kilojoules per mole, meaning if we want to break a mole of HH bonds, we will require 432 kilojoules. That also means that if we're going to form a mole of HH bonds, 432 kilojoules of energy will be released. So the value or the magnitude stays the same, but the sign changes. Illustrating the point made about bond order in the previous slide, note the difference between the CC single bond, which has a bond energy of 347, and the CC double bond, which is nearly double, versus the CC triple bond, which is even greater at 839. So bond energy increases with bond order. Now let's consider how this corresponds to endothermic and exothermic reactions. For a reaction to occur, we need to break reactant bonds. This is an endothermic process. We need to put energy in to take apart the reactants, to break the bonds in the reactants. We also need to form product bonds. Bond formation is an exothermic process, so when the bonds and the products form, energy will be released. If more energy is needed to break reactant bonds than is released when product bonds form, the reaction will be endothermic. Consider in this case we're putting in much more energy than we're getting out. Therefore, overall, it's an endothermic process. If less energy is needed to break reactant bonds than is released when product bonds form, the reaction is exothermic. In this case, we're putting in a smaller amount of energy than we're getting out. Therefore, overall, the net process will be exothermic. Looking at an energy diagram representing the same thing, consider this endothermic reaction. This dotted line here indicates the amount of energy required to break all of the NH bonds in the reactants. So we're taking apart 2 NH3 molecules. That means we're breaking 6 NH bonds. On this side, we see the energy released when the product bonds form. We form 3 HH bonds and 2 N2 bonds. Notice in this case, the energy required to break reactant bonds is much greater than the energy released when product bonds form. Therefore, the overall reaction will be endothermic. More energy was put in than we get out. On the flip side, here's an exothermic reaction. Here's the energy that goes in to break reactant bonds. Here's the energy that comes out when product bonds are formed. In this case, the energy we put in to break the reactant bonds is less than the energy we get out when product bonds form. Therefore, our net process will release energy. It will be exothermic. We can also quantify this and use bond energies to calculate an estimated value for enthalpy of reaction, or delta H. That calculation can be done using the equation shown here. In this case, we're taking the energy that went in to break reactant bonds and subtracting from it the energy we get out when product bonds form. Let's look at an example together. Here I'm asked to calculate the enthalpy of reaction for this reaction shown here. I'm going to start by calculating the sum of the enthalpy required to break the bonds in the reactants. So looking at the reactants, if I have 1 mole of this reaction, I'm going to need to break 2 moles of HH bonds and 1 mole of OO double bonds. Looking at our table on the right, we see that to break 1 mole of HH bonds, we need 436 joules. Therefore, 2 moles would be 2 times that amount. And then our OO double bond will require 495 kilojoules per mole. Adding this up, I find that I need to put in 1,367 kilojoules of energy to break the reactant bonds. Now let's calculate the sum of the energies of the bonds formed in the products. It's helpful to draw a quick diagram of our products here just to remind ourselves that 2 water molecules look like this. Therefore, we're dealing with 4 OH bonds in our products, or 4 moles of OH bonds, assuming that we're dealing with a mole of reaction. Coming to our table over here, we see that breaking 1 mole of OH bonds requires 463 kilojoules. Therefore, forming 1 mole will release that same amount. In this case, we're forming 4 moles, so we're going to do 4 times 463, which gives us a total of 1,852 kilojoules. In other words, when the products form, they release 1,852 kilojoules. Now going back to our original reaction, I'm going to take the energy that we put in to break reactant bonds and to subtract from that the energy we get out when product bonds form. Doing that math, I see that our overall delta H is 485 kilojoules per mole. In other words, 485 kilojoules will be released when 1 mole of this reaction occurs. It makes sense that the value is negative, meaning this is an exothermic reaction, since more energy was released when the product bonds formed than was put in to break reactant bonds. Here's one to try on your own. Pause the video here, and when you come back, I'll reveal the answer. Consider the fact that it might be helpful to draw a quick sketch of each molecule, just so you can keep straight what bonds you need to account for. Welcome back. Here's what you should have gotten. First, I calculated the energy required to break reactant bonds. Then I calculated the energy released when product bonds formed. Then I subtracted the energy released from the energy gained, and I ended up with a delta H of negative 151 kilojoules, meaning when 1 mole of this reaction occurs, it will release 151 kilojoules. Again, notice that we have gotten out more energy than we put in, so this should be an exothermic reaction, and the negative delta H is consistent with that. That brings us to the end of this video. Let's review our goals. First, we looked at how bond enthalpies relate to endothermic and exothermic reactions. Then we looked at trends in bond enthalpies, comparing single, double, and triple bonds. Then we learned to calculate enthalpy of reaction, or delta H, using bond enthalpies.